Let's get started with chapter 7. Topic of chapter 7 is kinematics of a closed chain. Closed chain is defined as a kinematic chain that contains one or more loop. If your mechanism has some closed loop, at that time we can call it the closed chain. For example, the planar Poba linkage is very well-known one, Stewart platform, and the delta robot. As you can see here, the Stewart platform is given in this figure. Delta robot is given here. Maybe you know that the degree of freedom of the Stewart platform, it has 6, is it right? One more, the delta robot system has the 3 degree of freedom. We have talked about them in the previous lecture. On the other hand, we can define the parallel mechanism. Parallel mechanism has the closed chain composed of fixed platform and moving platform connected by several legs. Okay, so the parallel mechanism is defined as a closed chain having fixed platform, moving platform, and several legs. Okay, the Stewart golf platform, sometimes we can call it the Stewart platform in short. Stewart platform is used as both the flight motion simulator and 6-axis pulse torque sensor. Maybe the flight motion simulator is the well-known example of a Stewart platform. But the Stewart platform has the small workspace and it has the many kinds of singularity. So if we use the Stewart platform, at that time we should be very careful to deal with the singularity and the workspace. The well-known delta robot is the 3 degree of freedom mechanism. In this case, the moving platform moves parallel way to the fixed platform. So the orientation is the same all the time with the fixed platform. So delta robot does not have any orientation variation. It just moves X and Y and Z. On the other hand, the delta robot has the actuator here, and here. Every actuator is located at the fixed platform, so moving part is very lightweight, so it can move fast. So the delta robot has 2 kinds of advantages, such as the moving part, very relatively lightweight, and it has very fast motion. Okay, let's review the several properties of a closed chain. Okay, the closed chain, not all joints are actuated. It means the mechanism has the passive joint. It does not have any actuator. It just consists of several bearing or level joint or universal joint without actuator. Second, the joint variable must satisfy loop closure equation. Okay, from here we will define the constraint Jacobian later. The third, the closure chain, it will be actuated, redundantly actuated or exactly actuated. Okay, many cases over the number of degree of freedom, the actuator can be installed. Okay, so the coordination of actuator poles is required. That would be one of the disadvantages of parallel mechanism or closed chain. The poles, new types of singularity, such as actuator singularity, configuration space singularity, and the vector singularity will appear in this mechanism. Those are different from the open chain. So if we use the closed chain, such as the parallel mechanism, we should be very careful in dealing with the singularity issue. Okay, for general closed chain, it's difficult to obtain the explicit set of equation for the pole kinematics. On the other hand, the inverse kinematics is very straightforward. Those issues are dual problem of open chain. In the case of the open chain, the pole kinematics is very straightforward, but inverse kinematics problem, it will be a little bit difficult to be hard to obtain. On the other hand, for the closed chain case, the IK inverse kinematic problem is very straightforward, very easy to obtain. But the pole kinematics will be difficult issue. Okay, so both are dual issue between the serial chain and closed chain. Okay. Okay, IK and FK of the closed chain. Okay, as mentioned before, for serial chain or open chain case, the pole kinematics is very straightforward, but the IK may be complex. So there are many solutions in the case of IK issue of the open chain. Some case there is no solution to calculate the IK problem. So those kind of issue is converted to the parallel mechanism. At that time, the issue is also converted. IK is very easy, but the FK is a little bit hard. Okay. For parallel mechanism, the IK inverse kinematics relatively straightforward, but the pole kinematics may be quite complex. Okay, it will be discussed in this lecture. Okay, let's take an example as opposed to one. Okay, 3-leg RPL planar parallel mechanism. Okay, this is a planar mechanism. Let's attach the fixed coordinate here. Okay, and 3-leg D1, D2, and D3. In here's level joint will be attached to here. Okay, and then prismatic D1, D2, D3, and another level joint will be attached to the connecting point. Okay. Okay, and then let's attach the body coordinate here. So let's write down the kinematics. In here, so we have the 3 closed loop closure equation. Okay, first one will be the A1 plus D1 will be equal to P plus B1. Is it right? From here, we have one closed loop equation, and A2 plus D2 will be equal to P plus B2. On the other hand, A3 plus D3 will be equal to P plus B3. From here, we have 3 loop closure equation. Okay, that will be denoted like this. 4, 1, 2, 3. Okay. Okay, here's we will attach the actuator to the prismatic joint. So 3 prismatic joint typically actuated, but the 6 remaining level joint are passive. Just to move if you apply some force to this mechanism. Okay, the length of each of the 3 legs will be denoted by the S. So the absolute value of the s can be obtained by taking a square root of this vector. Okay. The IK issue, the inverse kinematic issue is to determine the s from the position of a body frame, orientation of the body frame. Okay, so from TSB, we should determine the length of each leg s. Okay, that is the IK issue of this mechanism. From here, every vectors will be expressed in the S frame except B, is it right? So B will be expressed in terms of B frame. The other ones will be expressed in terms of S. On the other hand, A and B, A and A1, A2, A3 will be constant. Is it right? Okay, in terms of the B, B1, B2, B3 will be constant. So AI and BI will be the constant. Okay, so let's write down the vector equation using the S prime. So DIX will be the PX plus after multiplying the rotation matrix from S to B, and then the P vector will be multiplied to get some element of X prime, X axis of the S prime, and then the minus AX should be added to here. Okay. Okay, the Y part can be obtained like this. As you know, the rotation matrix will be expressed 2 by 2 using the one angle. In here's G directional angle. Here's denoted by the pi. Okay. Okay, let's obtain the S. Okay. S square will be the DI x square plus DIY square. Okay. So after obtaining this value, then we will take the square root operation to obtain the length of each leg. As mentioned before, DIX has the four terms, DIY also has the four terms like this. The IK issue can be written, as you can see this equation, the dx square plus dy square. So we can determine each leg length using this equation for given px and py and pi. Okay, if you provide the px and py, the body frame position and orientation pi are given at the time, we can determine the length of each leg. Okay, using these three equations. It's not difficult, so IK issue very easy in the case of a closed chain. On the other hand, the board kinematic issue is a little bit difficult. So the board kinematic problem of determining the body frame position and orientation from the leg length, it's not trivial, a little bit hard. Okay, the following in here to solve this issue. Okay, in here, we will provide the S, and then we should determine the px and the py and the pi. Okay, we have three equations. Then we will take the some tedious manipulation. Then we can determine the px and the py and the pi. Okay, those procedure is called as board kinematics. Okay, so let's introduce the half angle or tangent half angle substitution, because the pi, cosine pi and the sine pi must be the nonlinear function. So we will replace as a polynomial. So if you let the t as a tangent pi over 2, at that time the sine pi will be the 2t over 1 plus t squared. The cosine will be denoted by 1 minus t squared over 1 plus t squared. So these two polynomial will be applied here and here. Okay? Then we can write down the polynomial equation in terms of t and px and py for given s. So if you write down the three equation, this is a given value, and given value, and we should determine the px and py and t. Okay. Okay. Unknown is we have the three unknown. We have three equation. So we can write down we can solve this kind of nonlinear equation. Then we can get the px and py and t. But if you manipulate these three equation, then we can get the sixth order polynomial in time t after removing the px and py. Then we can get the t a polynomial as a sixth order. It means the fourth kinematics will provide six solutions. Okay, such as it is very similar with that the inverse kinematics of the open chain will have many solution or no solution there. Those kind of concept is applied to the fourth kinematics of closed chain. Okay. One more, we will deal with the simple case of singularity. Okay, every leg has the same length. The lengths are identical each other. At the time, if you apply the linear force here, here, and here, maybe this moving plate can rotate left side or right side, clockwise or counterclockwise. We don't know that. We cannot predict it. Okay, so this kind of case is called as bifurcation. Okay, we cannot determine the clockwise or counterclockwise. It is corresponding to the singular configuration. Okay, so the leg lengths are the same each other. Then we have a singular configuration of the closed chain. Okay, in the case of the B, here the leg lengths are same each other, but the angle is a little different from the previous one. Okay, let's consider the leg lengths are given the same, but we have the two kinds of solution. So the fourth kinematic solution are given as a two. I'm sorry, my computer is responding to my voice. The shitty. Okay, I turn off the computer now. Okay. Okay, like this, as shown in figure B, we have two solutions to the fourth kinematics when all leg lengths are identical. Okay. Okay, let's take another example. Stewart platform. Okay. Let's consider Stewart platform. This point. I'm sorry. Okay. This point is the fixed plane denoted by the S, and then AI as a constant vector, and then DI. Okay, the sum of the AI and DI will be equal to P plus BI. the same equation with the planar case will appear. So di will be equal to p plus pi minus ai. We have the sixth equation, okay? Because this tilted problem has the sixth leg. Okay, here the p vector will be denoted in terms of the body frame. So we should multiply the rotation matrix from S to B. So rotation matrix appear here. Okay, similar with the previous example, the leg length squared will be the d transpose d. It can be obtained these two equations. Okay, in here, for given p and r, okay, in here, p will be 3 unknown. I'm sorry, the 3 will be given, and then the r will be given as a 9 element. Actually, the 3 elements are independent. 6 element is dependent because the r transpose r should be equal to identity. It means this equation has the 6 dependent equation. Okay. For given p and r, okay, if we apply the p vector and the rotation matrix of the b, those are given by the user. At the time, the 6 leg length SI can be obtained straightforward. Okay, can be determined directly from this equation. Okay, so in other words, IK issue very easy. On the other hand, the leg length is given. For given each leg length SI, leg length is given, we must solve the position vector P and the rotation matrix. As you can see here, the position vector has the 3 unknown. Rotation matrix has the 9 unknown, but it has a 6 dependent equation. Is it right? Because R transpose R should be equal to identity matrix. Okay, anyway, we needed to have 12 equation to solve the P and the R. Okay? Like this, the pole kinematic issue is not easy. Okay, for given S, we have the 6 legs, so we have 6 equations. Here, we should determine the P and the R, okay? 12 unknown. But as mentioned before, R transpose R should be equal to identity. Okay, so R and R transpose is given, should be identity. From here, the first element should be 1, okay? The second element should be the 0, okay? The third element should be 0. And the second element should be 1. The last element, the 2 by 3 element should be 0. Like this, we can write down the 6 constraint. Okay, from here, we have 6 equation. As mentioned before, the P has 3 unknown, R has 9 unknown, so 12 unknown. But we have 12 equation. It must be the nonlinear equation, but we can solve it. Maybe it has the multiple solution for the kinematics, because as you can see here, this equations is not easy to be solved. Okay. Anyway, we have 12 unknown, we have 12 equation. So the solution must exist in this equation. Okay, let's extend this kind of concept to the general parallel mechanism. Okay, here the fixed frame is attached to the ground, and the leg 1 has theta 1 through theta m. M joint are applied, but we don't know though which one is activated, which one are passive. Anyway, the second leg 2 has the pi 1 through pi n. N joint exists in the leg 2. Leg 3, psi 1 through psi p. So all the joint will be the m plus n plus p. Okay. The body frame is attached to the moving platform. Okay. Let the configuration of a moving platform be given by TSB. Okay, this is a formal description for the orientation and the position. It has the 12 unknown. 12 known or unknown. It depends on the body kinematic or inverse kinematics. Anyway, it has the 12 independent, the 12 variable, the 6 independent. It means 6 independent, 6 independent. Okay. Okay, let's denote the pole kinematics of the 3 chain by the T1 and the T2 and the T3. Okay, by using the POE, we can write down the homogeneous transform of the T1 through T3. Okay. Okay, the body frame should be equal to each other. So we can find out 2 constraint equation from here and here. Instead of this equation, you can choose this one. Okay. It does not show any difference. Just you can choose 1 and 2. Okay. So we have 2 matrix equation. Okay. This equation has a 12. This matrix has the 16 element, but we have the 4 variables 0, 0, 0, and 1 as a last law. So it has 12 equation. On the other hand, T2, this equation has also 12. Okay, but it has the 6 dependent and the 6 independent. It has 6 dependent and the 6 independent. So from the both equations, we have 12 independent equation. Is it right? But this 3 leg will have M plus M joint and N joint and the P joint exist. So from these 2 equations, we can obtain the 12 independent equations. So minus 12 is required to obtain degree of freedom of this mechanism. Okay. If you choose the M, N, P as a pipe, this mechanism will be 3 degree of freedom. Okay.